Welcome to my channel Phi Concepts CHM. We will see the seventh part of the series of electrical properties of metals. Here we will see about thermionic emission, where we will derive the Richardson-Dushmann equation. Thermionic emission, Richardson-Dushmann equation. When a metal is heated to sufficient high temperatures, electrons are emitted from its surface. From the figure, at T is equal to 0 degree Kelvin, all levels up to EF are filled and above EF are empty. Also, electrons at EF cannot escape from metal because of presence of energy barrier at the surface. Height of the barrier is phi, which is the work function of metal. As temperature is increased, electrons which can surmount the energy level EF plus phi can escape from the metal. Let x direction be perpendicular to the surface of electron emitting solid. Momentum in x direction so as to just escape from the solid is given in the form as P suffix x0 square by 2m is equal to EF plus phi. EF plus phi is the barrier height V suffix B. So this can be written as Px0 square is equal to 2m into EF plus phi. Let n of Px be number of electrons per unit volume having momentum values between Px and Px plus dPx in x direction, where electron having momentum Px arrives at the surface with the velocity is equal to P suffix x upon m. Number of electrons arriving at unit area of surface in unit time can be given as integration of Px upon m into n of Px dPx with limits Px0 to infinity. Hence, the emission current density is given as small j is equal to E by m into integration of Px into n of Px dPx with limits P suffix x0 to infinity. Now n of Px dPx is the product of the number of possible states of momentum between Px and Px plus dPx and probability of finding an electron in each state. So we can substitute E is equal to P square by 2m by differentiating this. dE is equal to P dP by m. Substituting these two in this equation, Z is equal to pi by 2 into 8m by h square the whole raised to 3 by 2 into E raised to half dE. We get Z of P dP is equal to pi by 2 into 8m by h square the whole raised to 3 by 2 into P square by 2m the whole raised to half into P dP by m. So the equation 3 becomes, by solving these steps, we get Z is equal to 8 pi by h cube into P square dP, equation 4. Consider a spherical shell with radius P is equal to square root of Px square plus Py square plus Pz square. P is the momentum along the respective axis with dP as thickness. Fraction of states having momentum between Px and Px plus dPx, Py and Py plus dPy, and Pz and Pz plus dPz, that is the fraction of states in dPx into dPy and dPz, is equal to dPx dPy dPz upon 4 pi p square dP. This is the numerator is the volume of a cell and denominator is the volume of the spherical shell. Total number of states in the momentum interval dpx, dpy, dpz is equal to the total number of states in the momentum interval dp into the fraction of states. So this is equation 4, 8 pi by h cube into p square dp, and this term we get from here dpx, dpy, dpz upon 4 pi p square dp. We get 2 by h cube into dpx, dpy, dpz, equation 5. Number of electrons per unit volume having momentum values between px and px plus dpx in x direction is given as n of px dpx. Substituting equation number 5, you get 2 by h cube dpx. We are keeping this outside the integral. In then integration of dpy dpz upon 1 plus e raised to e minus ef upon kt. First we will integrate with respect to y and z. We will integrate with respect to x later. So hence the x terms are kept outside the integral. So there are double integrals with limits py is equal to minus infinity to infinity and pz is equal to minus infinity to plus infinity. As e minus ef is very much greater than kt, therefore 1 is neglected. And also e is equal to 1 by 2m into px square plus py square plus pz square. So we can write this as 2 by h cube into dpx, double integrals from with limits minus infinity to plus infinity. This is e raised to minus e by kt, as this one is now neglected. So we have taken these the exponential in the numerator. So e raised to minus e by kt into e raised to ef by kt dpy dpz. Then e can be substituted as px square by 1 by 2m into px square plus py square plus pz square, that is substituted here. E raised to ef by kt is a constant, so it is taken outside the integral. Also the term in x, that is e raised to minus px square by 2m kt, is taken outside the integral. And now we will integrate with respect to y and z. So we'll use the standard integral, integration of e raised to minus alpha x square dx from with the limits minus infinity to infinity is square root of pi by alpha. So you get this as square root of pi by 1 by 2m kt into square root of pi by 1 by 2m kt. 2m kt can be taken in the numerator, so this will be square root of 2 pi m kt into square root of 2 pi m kt. So this becomes, multiplying both, we get 2 pi m kt. So the final equation is 4 pi by h cube m kt into e raised to ef by kt into e raised to minus px square upon 2m kt dpx, equation 6. Substituting equation 6 in equation number 2, that is the equation of emission current density, J is equal to E by m integration of 4 pi m kt upon h cube e raised to ef by kt into e raised to minus px square upon 2m kt px into dpx with limits px0 to infinity. From equation 1, px square by 2m is equal to ef plus 5. Differentiate this equation, so you get 2px dpx upon 2m is equal to d5 as ef is a constant. 2 will get cancelled out, so you get px dpx is equal to md5. Substituting everything, we get all these are constant. Then e raised to ef by kt, e raised to minus ef plus 5. This is px square by 2m. We are substituting minus ef plus 5 divided by kt, and px dpx is md5. So this can be written as in the integral. Inside the integral, it will be e raised to ef by kt into e raised to minus ef by kt into e raised to minus 5 by kt into md5 with limits 5 to infinity. That is corresponding to px0 is the energy 5. px0 is the minimum momentum required for the electron to escape, and corresponding to that the minimum energy required is 5. So both these will cancel out. M will cancel out. So what we get is 4 pi me kt upon h cube integration of e raised to minus 5 by kt d5 with limits 5 to infinity. Integrating the exponential, we get minus kt into e raised to minus 5 upon kt with limits 5 to infinity. This kt is taken outside. Substituting the limits, we get e raised to minus infinity minus e raised to minus 5 by kt, where e raised to minus infinity is 0. So you get only minus of e raised to minus 5 by kt. This minus and this minus we have taken here outside. Here both will, this becomes plus. So what you get finally is 4 pi emk square upon h cube. This whole thing is a constant into t square e raised to minus 5 by kt. So this whole thing can be written as a constant a. So j is equal to at square into e raised to minus 5 by kt. This is called as a Richardson Dushmann equation, where a is equal to 4 pi emk square upon h cube. Rearranging the equation, we can write j by t square is equal to a e raised to minus 5 by kt. Taking the log of j by t square is equal to log a minus 5 by kt into 1 by t. This 5 by kb is substituted as b. Using this equation, we can plot a graph of log j by t square versus 1 by t. The graph shows a straight line with slope as minus 5 by k, intercept as log a. The work function phi depends on the electric field and decreases with increasing field strength. Emission current depends on the surface conditions. Contamination of surfaces drastically change phi. Thank you for watching my video.